Yeah, there you go. Hi. So yeah, I'm Drummond McCulloch from the Neurobiology Research Unit, part of the Danish Center for Psychedelic Research at Copenhagen University Hospital, this beautiful building here on the right where I'm very privileged to work. So I'm going to be talking to you today about psychedelic neuroimaging and chaos in a couple of different ways in that field. Just a quick conflict of interest statement. So I won a financial award from Compass Pathways a couple of years ago. So they pay for my PhD stipend, but I don't work for them. It was like an award sort of system. I don't report to them and they don't tell me what to do. Okay, so we start off by asking the big question and why I think it's important that we talk about this. Why should we bother spending so much time and money and expertise investigating the acute effects of psychedelics on the brain? And so now I'm going to present a bit of a model that the way I think about this. So let's take the depressed brain, for instance. It's low mood, it's stress reactive. And we know that in about a third of people, and you administer SSRIs, say sertraline, for 6 to 8 weeks, over time, gradually that brain will move to a state of well-being, normal mood, normal stress reactivity. This works for about a third of people. It has some issues with side effects, as we all know. There's also other drugs out there, like cocaine, which can take the depressed brain, and over the course of about a minute, take them into this place of just confidence, exuberance, joy. But then about 15 minutes, maybe 20 minutes later, they return to the depressive state, and in some cases, they may even be returned to a worse depressive state. And that's pretty interesting from a psychopharmacology point of view. So now we have this new paradigm in the space, where when we take maybe the depressed brain, but also the healthy brain, and we administer a serotonergic psychedelic, like psilocybin or LSD, over the course of maybe 2 hours, maybe an hour, if you smoke DMT, maybe over the course of 10 minutes, you go into this sort of other brain state. And this is a quote from one of our participants that I think captures some of the nature of this brain state well. She said, "The light of love brings clarity to everything. I get a deep feeling of purity and feel that everything is beautiful and that love is what makes up the world and the universe and connects everything like a network of roots." So that's beautiful, right? But usually in pharmacology, when you administer a drug, say cocaine, you get the inverse effect happening in the backlog. So you say alcohol is like borrowing confidence from tomorrow, or caffeine is like borrowing sleep from tomorrow. But for some reason, with psychedelics, and this isn't the case for everyone, as we heard this morning, there's some real complexities into all this. But for some reason, people don't go from this place of love and connectedness and joy. As a classical pharmacologist, if I'd never heard of psychedelics, I'd say, yeah, but tomorrow you're going to feel isolated and you're going to feel loveless. But for some reason, people go the other way. They go to this healthy brain state on the far side. At least some people do. So to me, that makes it extremely interesting to work out this psychedelic brain state and what's going on in the brain there. It's not just positive mood like we have with cocaine or with other drugs. So this is why I hope you can agree with me that it's very important that we understand what changes in the brain when we give these drugs. Okay, this isn't a new idea. So what's been done so far? Between about 2012 and this from last year, there have been about 50 studies. And almost all of them have been looking at these acute effects. We summarized all of these findings and how they've all worked and how they've all played off each other in a review last year with all of the PIs who co-authored these papers. But there's one big problem, and that over these 50 papers, almost nobody has done the same thing twice. So these are all what we would call phase 1 neuroimaging studies. So in the drug development world, when you identify a new and exciting drug candidate, you first put it into phase 1, you put it into healthy people, and you just sort of look and see what it does, and you develop some hypotheses about how it works. Then you go into phase 2, where you start testing your hypotheses. Phase 2B, you increase your sample size, you refine your testing from multiple angles, and then you go into phase 3 to really check whether the drug does what you think it does and how it does it. With neuroimaging, and specifically at the moment with psychedelic neuroimaging, we're stuck in phase 1. We keep finding a new and interesting biomarker, and then going, that's cool, putting it on the shelf, and then looking and finding another new and interesting biomarker and saying, that's cool too, and then putting it on the shelf. But we've never actually revisited any of these interesting biomarkers from before. So we're stuck in phase 1. However, there has been, even though no one's really doing the same thing, there have been some emerging hypotheses in the space that have come out of this. So today, I told you I'm going to be talking about chaos. We're going to be talking about the entropic brain hypothesis, which I think is probably the most prominent hypothesis in the space. It's definitely the one that's been specifically claimed to be tested the most. So this was proposed by Robin. I think this photo is hilarious, by the way, because he's like got a needle on a mushroom. It's not going to do anything. So he proposed back in 2014 this idea in this paper called The Entropic Brain, Theory of Conscious States Informed by Neuroimaging Research with Psychedelic Drugs. And then he revisited it in 2018, and I have it on good authority that there's going to be another revision coming out in 2024 sometime. So in this most recent edition of the entropic brain hypothesis, it's articulated as such. And I'm going to read the whole thing out, and I realize that that's maybe a bit much, but we're going to go through it step by step, so it's important that we understand it. So he says the qualia, or subjective quality of any conscious state, and specifically the richness of its content, can be indexed by a quantitative measure of the magnitude of entropy in the information theoretic sense in a given parameter of spontaneous brain activity. Okay, that's a lot. Let's start with the first bit where he says the qualia and the richness and so on and so forth. And let's just condense that right down. We're using psychedelics as tools here to test this hypothesis because it's assumed, and let's just leave that assumption for now, that psychedelics increase the richness or the qualia or the subjective quality of a conscious state, right? Like for now, let's just agree that that is the case and put it off to the side. And let's start breaking down the rest of it. So what's entropy? And you probably all have some sort of sense of what entropy is. It's like a sort of chaoticness, messiness, something like this. But the way that I think it to most clearly conceptualize entropy is in 3 ways. Diversity, how much variation there is in the system. Unpredictability, so not knowing what comes next. And complexity, how much information it requires to describe a system. So from a conceptual point of view, this is what entropy can really be thought of, where represented by the images on the right. Okay, but what Robin didn't just say the entropy of, he said a quantitative measure of the magnitude of entropy in the information theoretic sense. So in order to get into the information theoretic sense, we turn to the father of information theory, Claude Shannon, who developed an equation wherein you can put a number on how entropic something is. And we move here from concepts to maths. This is a scary looking equation, so let's use some nice examples. So in California, where Robin now lives, the weather is stable, it's predictable, and it's simple. It's sunny 90% of the time, and it's cloudy 10% of the time. In Copenhagen, where I live, the weather is diverse, unpredictable, and complex. Unlimited because there's only 5 columns here. Really, it should be like as wide as the slide. But it could be any weather at any time. And so the way this equation works is you pretty much add together the height of each column multiplied by the log of that column. Don't worry too much about the maths. So for the one on the left, for the weather in California, you'd take 0.9, which is the probability of it being sunny, multiply by the log of 0.9, and then add that to 0.1, the probability of it being cloudy, by the log of 0.1. Similarly, for the weather in Denmark, we take 0.2 times log 0.2, 5 times, and we add it together. And so what we can show here is that quantitatively, the weather in Denmark is more entropic because it has an entropy of 2.32 bits as opposed to the weather in California, which has an entropy of 0.47 bits. You guys with me, generally? Nice, all right, sick. Okay, so the last part of Robin's definition of the entropic brain was he said, the entropy, blah, 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 of a given parameter of spontaneous brain activity. And so what this has mean, because this is nice and non-specific, this means that some studies have investigated using electroencephalography, EEG, and some studies have investigated it using functional magnetic resonance imaging. There's also one that's used magnetoencephalography, but that's hard to say, so I'm not going to focus on it. I'm also not going to focus on EEG for now, because it's a less fun story. So let's talk about fMRI. So 12 papers out of those 50 that I discussed earlier have actually specifically articulated that they've evaluated the effects of psychedelics on entropy in fMRI. That's awesome, right? Like, we're doing science, we're making hypotheses, we're testing it over and over again. Nope. Every single time someone has tried to test this hypothesis, they've used totally different maths to do it. So each of those 12 papers has now 12, actually 13, entropy metrics. But then you're looking at me like, wait a second, you just said that there's like a way of determining entropy. How can there be 12 papers all doing it differently? It's a good question. Thanks for asking it. Let's go back to this slide with Claude Shannon, the father of information theory. So I told you that we were looking at the entropy of the weather earlier, and we looked at the different weather states. But we could just as easily have looked, for example, at the temperature and how that varies across time. In Copenhagen, we get down to -10 and up to 38, apparently. And in California, it's like pretty much always hot. So in this case, we would also say that the entropy of the weather is higher in Copenhagen. But we've taken the entropy of two different faces of a complex system. We could also look at, for example, precipitation and how many days it rains a certain amount, or wind, right? This one, I think, is important to highlight that the entropy measure measures the width of the histogram, how broad it is, and not actually where it is. So even though it's windier in Denmark, the distribution is as wide as it is in California, and so the entropy is the same. I just wanted to highlight that quickly. But this is also just to say that like the brain, oh no, other way around, like weather, the brain is a complex system. And with a complex system, you can analyze many different facets of it and populate your histogram with lots of different values. Okay, I forgot how extra that slide transition was. What did we do? We looked at the 12 different papers, and we raked through their supplementary methods sections, and we found exactly what we thought was the maths behind each one of these. And you can see in a lot of these diagrams here, this is super busy, please don't try and understand all of this, there's a histogram, but it's a different thing in each of those histograms. So once we thought we had a pretty good idea of that, we wrote to all the original authors and we said, hey, this is what we think you're doing, is that right? And then they all responded to us. Eventually, this took like 6 months of back and forth. But then we had all the code, and this is all freshly written code, pretty much. And then we took all of these 13 different metrics, and we turned them into the Copenhagen Brain Entropy Toolbox. Woo! All right. So now we have a toolbox that contains all of the different entropy measures that we can apply to any neuroimaging data if we need it. But wait, we don't have any neuroimaging data. So we recruited 28 individuals in their early 30s, healthy people, and we put them in an MRI scanner, and we scanned their brains for a bit. And then afterwards, we asked them, how intense is your experience right now? And they said, that doesn't make any sense, you've not given me any drug yet. We said, that makes sense. And we took a blood sample, and we checked if there was any psilocybin or psilocin in there. And once again, we hadn't given them drug yet. So we gave them drug. And this is quite a high dose of psilocybin. And then we scanned them again. So about 50 minutes afterwards, we scanned them again, and this time we asked them, how intense is your drug experience right now? And they said, yeah, I'm getting high. And they got a blood sample as well. And then we scanned them again at 90 minutes, and we scanned them again at 140 minutes, and we scanned them again at 300 minutes. So what does this look like on the curve? Well, on the x-axis here, you can see the time between the drug administration and the thing that we're asking. And on the y-axis, you can see the subjective drug intensity. So we can see that a lot of people went up to 10 out of 10 intensity and generally peaked around 100 to 150 minutes. And we scanned them, like I said, at baseline, once during the ascent phase, once during the peak phase, once during the descent phase, and then finally once people were largely sober again. So what we were trying to do is capture the entire dynamics of the brain over the course of the psilocybin session. And if you're wondering what it's like to be in a scanner while on psilocybin, this is a report from one of our participants. And she said, "I felt a sense of no longer being connected to my own body. The MRI scanner and I stepped into a different reality together with colors and shapes and figures." And this drawing here, I don't know if anyone's been in has anyone here been in an MR scanner? Pretty much it's just going like the whole time. And these are all the different sequences, because sometimes it's a longer beep, sometimes it's a shorter beep. I don't know. I just think this is cool. Right. So what I'm about to show you is a table comparing our study with the previous studies. And I want to really emphasize that this is not a hit piece on these previous studies. We are absolutely standing on the shoulders of giants, of these pioneers who went out before us and said, I bet we can give people psilocybin while they're in an MR scanner. It's a crazy idea. So I just want to give absolute credit to all the previous studies. But with that said, let's show how we did it way, way better. So all the previous work has administered psilocybin or LSD intravenously, which is, well, it works, not the general method for administering psychedelics. Or they've administered ayahuasca, and with ayahuasca, you don't really know precisely how much psychedelic gets into the system at any given time. So we administered psilocybin orally. Previous work had small sample sizes. Like I say, these are phase 1 biomarker identification studies with 9 to 15 people. We had a less small sample size. I'm not calling our results confirmatory, but it's less small. We have 28 individuals. Previous studies didn't take any of these objective measures because it was difficult to, and we took the plasma drug levels. Previous studies looked once before and once after. And then when they do the statistics, they say, is scan B different from scan A? And if so, how? We did, like I described earlier, 4 of these post-drug scans. And what that allows us to do is, in our statistics, instead of saying, is drug different from not drug, we can say, is the amount of drug in their system associated with changes in brain entropy? And so we get a more nuanced understanding of the relation between psychedelic effects and brain entropy effects. Finally, and the whole purpose of this thing, each previous study reported 1 entropy metric, and we've reported 13 because we're trying to get a grasp on all of these different entropy metrics. Okay, so we have our toolbox and we have our data. What questions were we asking of this data? So our first question was to resolve whether all of these different entropy metrics were actually all measuring the same central construct. You can imagine it being the case that brain entropy is a singular thing, and you can quantify it in lots of different ways, like measuring the temperature in a number of different ways. Or it could also be the case that each of those different entropy metrics are measuring a totally different thing, and that this type of brain entropy actually has nothing to do with this other type of brain entropy. And then there's a sort of middle ground where some of them are like a cluster of entropy things, and some are a cluster of a different cluster, but they move independently. So that was our first question, to resolve whether we're all testing the entropic brain hypothesis. Secondly, if those entropy metrics were distinct, we wanted to test which of them was most closely associated with the psychedelic effects, because like I said earlier, I think it's important that we understand what the psychedelic effects are on the brain. So, what did we find? Well, the first question was a little disappointing, because there's pretty much no correlation at all between any of these entropy metrics. There's some that are based on very similar maths here, and those are the 2 orange squares near the diagonal. But some of them are even anti-correlated, where some of them, if the entropy goes up for one of them, it goes down for the other one. We did a bunch of fancy statistics on this as well, principal component analyses, all of this sort of stuff. There is no structure within this data. And so disappointingly, it's not like we've tested the entropic brain hypothesis a lot. We've actually just tested 13 different entropic brain hypotheses once each. But reassuringly, this is now interesting, because now what we have are 13 different distinct entropy metrics. And then that can maybe tell us more about the brain, because then we can say something more nuanced than psychedelics increase brain entropy. We can say something like psychedelics increase this specific type of brain entropy. And that's an exciting thing, I think. I hope you agree. So, I really hope you do agree, because we're going to spend the next 20 minutes going over it. So if you don't, like, go get a drink of water or something, I don't know. All right, cool. So over those 12 different entropy metrics, 4 of them measured the entropy of the static connectivity in the brain. I'm not going to go into it in too much detail, but when you do fMRI imaging, you can use the resultant data to say that brain region A is connected to brain region B with a strength of 0.7, but brain region A is connected to brain region C with a strength of 0.2. And then you take the average over your entire scan, and you can create effectively a map of the brain of how connected all these different bits of the brain are. And then you get what's called a static connectivity map. So I think of that like these castellas that they make in Barcelona, where they're not moving, but we know who's connected to who. So there's 4 different entropy metrics in this subdomain. 3 of them show absolutely no relation to plasma drug levels. But I think this is a good opportunity to walk you through these figures, because I'm going to show you a bunch of them. So on the x-axis here, we have the plasma psilocin level. This is how much drug is in the system. We've previously done PET imaging studies that show that the amount of drug in our plasma is very closely associated to the amount of drug that's in our brain. So we can use this as a metric for that. Then, on the y-axis, we have the entropy metric. And this is different for each different plot. This is degree distribution, von Neumann entropy, and out-network connectivity. We're not going to go into these, but that's what they are. The color of the dots represents when the scan was taken. So the black dots are the pre-drug scans, and then the purple and the pink dots are around the peak drug effects, and then the orange ones are that late scan when people are kind of sober again. And this would allow us, if it was there, to see any sort of hysteresis effect, where you can imagine that the entropy increases and then stays up, or something else like that happens. Okay. That's you pretty much walk through, and then I have some p-values in here as well. I'm happy to talk about the statistics afterwards if people want to. So 3 out of the 4 static connectivity entropy metrics were not associated with psychedelic drug effects. That's a little sad. However, this one, called path length distribution, showed a weak to moderate-ish correlation with the plasma psilocin levels, and the p-value indicates that there's something here. So I'm going to walk you through specifically what path length distribution entropy is. The question that path length distribution entropy asks is, how diverse is the connectivity pathing across the whole brain? Well, what do I mean by that? Well, I told you that using fMRI, you can determine to say this brain region is connected to this brain region, or this brain region is not connected to this brain region. So you do that for the whole brain, and you construct a graph where you show edges between things. Imagine that there's 10 brain regions, right? So we have one on the left and one on the right, and these are from different scans. Next, you calculate what's called the path length between each pair of regions. So say I'm at region 8, and I want to get to region 6, right? On the left-hand graph here, if I want to get from 8 to 6, I go from 8 to 1, and then 1 to 6. My path length is 2. On the right-hand one, this was a bad example. Oh, well. On the right-hand one, say we're at 8, and we want to get to 6, we go from 8 to 9, and then 9 to 6. Again, the path length is 2. That's why that's a bad example. Trust me, it varies. We then take all of the different combinations of path lengths, getting from 9 to 1, 9 to 2, 9 to 3, 9 to 4, and so on and so forth. And then we plot a histogram of the path lengths, and then how many times it was that path length. And then you guys know what to do. When you see a histogram, you calculate the Shannon entropy of that histogram, estimating the width of it. So how do we interpret this? When the Shannon entropy is low, that means that there's either only short path lengths or only long path lengths, but the distribution is very narrow. They're all very similar to each other. However, when the entropy is high, that means that we have some short paths, some long paths, and some middle length paths. And let's remember that when you give, when plasma psilocin levels increase, when psychedelic drug effects are on board, this goes up. So it means we move towards a state where we have some short, some medium, and some long path lengths. What does this mean? I don't know. But I am super open to people interpreting that. It's really mind-bending-y. So yeah, let's have a beer and talk about it later. So the next subsection of entropy metrics, I'm dubbing dynamic connectivity. And the way to think about dynamic connectivity is, as before, we can use fMRI to estimate how two brain regions are communicating with each other at any given time. But now, instead of just looking at what that connectivity structure is, we look at how that connectivity structure changes over time. So at time point A, regions A and B are really connected, they're really talking to each other. But then at time point B, they're not talking to each other. At time point C, maybe they're talking to each other a little bit. So that's to do with how the connections change over time. So I think about this like a ceilidh. I'm Scottish. This is a traditional Scottish dance, where sometimes you're dancing with one person, sometimes you're dancing with another person, sometimes you're not dancing with anyone. So we think about how that's going on in the brain. There's 6 entropy metrics here. 5 of them show absolutely no relation to plasma drug levels. It's all calm, as far as this entropy is concerned. But one of them shows what I think, and you should, at this point, everyone just start standing up and applauding, because this is the strongest correlation. No, please don't. This is the strongest correlation I have ever seen in fMRI. fMRI is noisy. There's a lot of, it's crazy that we can use magnets to determine how much oxygen is in different bits of the brain, and that's a noisy system. This is as good a correlation as you're ever going to get. When plasma drug levels increase, dynamic conditional correlation entropy within the default mode network really increases. And if we just looked at the default mode network, we'd be like, the DMN, man, that's like it. That's how psychedelics work. But then we look at the whole brain, and it turns out that it's just the entire brain. Dynamic conditional correlation entropy increases, except within the motor cortex. And that reductionist bit of my brain just immediately goes like, yeah, of course, because everything's messed up, but people can still walk, right? So that makes sense. I don't know. We'll see how it goes. So dynamic conditional correlation entropy increases across the entire brain, except the motor cortex. But how does that work? The question that DCC entropy, we're going to start calling it that for brevity, asks is how diverse is the connectivity between regions across the scan? So we're talking about the variation across the scan. Bear in mind the scan is about 10 minutes long. This is the schematic of how it works. So step 1, you group the brain into regions, and then you get regional time series. So we get a different time series for each region in the brain. We then use some fancy maths called GARCH framework to calculate at every time point what the connectivity is between those regions. We then, for that region pair, look at every single time point, we look at the connectivity scores, and then we plot those connectivity scores just for those 2 regions on a histogram. We have a histogram, we calculate Shannon entropy of that, and then we have the entropy of the connectivity of that region pair. And then we take the mean across all of the networks to get that figure that I showed you before. So how do we interpret this? When this is low, it means that your region pair is either always connected, always disconnected, or always somewhere in the middle. Either way, it's stable. You're dancing with the same person in the same way over the entire scan. When this is high, it means that sometimes you're dancing with one person, next you're dancing with the next, you're dancing with another person. It's constantly changing. So this means that under psychedelics, it's not that we can just say that the connectivity is altered per se, but what we should say is that the connectivity is highly dynamic. it changes over the course of the scan in a way that it doesn't when we're sober. And that's a fundamental distinction from saying that there's changes in connectivity writ large. And let's just remember, just stand in awe at how awesome that correlation is. All right. The last subsection of entropy metrics I want to talk about is regional dynamics. So now we're no longer talking about connectivity. We're just talking about how the activity within a given region varies by itself over time. And this is akin to someone dancing by themselves, right? How do they move? How do they evolve over time? There's two entropy metrics in this one. One of them has two subsections. Neither of them are particularly significant. However, one of them is kind of interesting in the context of all the EEG research. If you want, if we have some time, my presentation is not that long, we can talk about this later. I think it's pretty cool. But this other entropy metric, I think, might actually be the most interesting so far, and that's why I've saved it for last. So on the left here, we can see again plasma psilocin level on the x-axis, and then what's called sample entropy at scale 1 within the control network. And we can see that as plasma drug levels increase, this increases. And then for sample entropy at scale 5 in the control network, say, plasma psilocin levels increase and this entropy decreases. So now we're going to have to go into what all of those things mean. So sample entropy is a measure of how predictable the signal is. And remember, we're not talking about connectivity here, we're just talking about the signal itself in any given network. So here our regions are networks. It's also a little bit refreshing that this effect also is across the entire brain. So we don't need to go into what control C is. Let's just consider that this effect is pretty much across the entire brain. Where at scale 1, we see increases in entropy. I should make a quick thing clear. These dots here represent the angle of the slope of those previous plots that I've been showing you. So when we have a dot above the black line, that means it's a positive slope. And when we have a dot below the black line, that means it's a negative slope. So at scale 1, as plasma drug levels increase, entropy increases. At scale 5, as plasma drug levels increase, entropy decreases. So like I said, sample entropy is a measure of how predictable the signal is in each network. And we can interpret it as that when it's low, we have predictable, low entropy, and when it's high, we have unpredictable entropy. Okay, now I'm not entirely sure, I haven't met a lot of you in the audience. Do we want to go through the maths of how this is calculated? Can I get a quick show of hands for yes? All right, okay, you asked for it, that's fine. Let's take a sample series. 0.5, 0.6, 0.5, 0.6, 0.7, 0.4, 0.6, 0.7, 0.5, 0.6. This is what it looks like. Then we have some parameter choices. This is often the case in maths. We just have some random parameters that you just have to choose. So we're going to take subsequences of length 2, and we're going to have a similarity threshold of 0.2. So what do? First, we take our sequence, 0.5, 0.6, 0.5, 0.6, and we split it into subsequences of length, subsequence length, right? So in this case, 2. So on the right here, you can see that that's the first and the second element, and then the second and the third element, and then the third and the fourth element. You guys are following? We split into subsequences. Okay, then we're going to compare all of those subsequences to each other to see how similar they are. So let's compare subsequence 1, which is 0.5, 0.6, with subsequence 2, which is 0.6, 0.5, right? 1 and 2, first and second element versus second and third element. We calculate the absolute difference element-wise. So the first element of subsequence 1 is 0.5, and the first element of subsequence 2 is 0.6. So the difference is 0.1. And then we look at the second element, and that's the same. The difference is 0.1. Then you take the maximum of the differences, which is 0.1, because they're both 0.1. And then we check if this is less than our similarity threshold, which we articulated before, which is 0.2. 0.1 is less than 0.2, so that's true. Therefore, we have a match. Cool. Then we do this for every single subsequence pair. So subsequence 1 versus subsequence 3 versus subsequence 4, and so on and so forth, for all of them. And we just count how many matches we have. Then we divide that number of matches by the maximum total number of matches that hypothetically could exist, right? If it was all just ones, everything would match, and that would be the maximum number. So we say what percentage of the sequences, subsequences match. This is considered then the repetitiveness for subsequences of length 2. Let's call it B. I appreciate that's confusing. We then repeat the process, but we make the subsequence 3. So instead of having the first and second, second and third, we have first, second, third, fourth, fifth, sixth for the subsequences. And we do exactly the same procedure, where we compare them element-wise, we take the maximum, we see if there's matches or not. This is then considered the repetitiveness for subsequence of length 3. Let's call this A. The sample entropy is the negative of the natural log, which is just a scaling factor, effectively, in this case, of A, the repetitiveness for subsequences of length 3, over B. And what this is conceptually, we can think of this as B is how repetitive is it when you've got subsequences of length 2, and then the repetitiveness when you increase the demand on that repetitiveness, right? Because it's always going to be lower when you have a subsequence of length 3, because you just have more things to compare, and then you take the max. So by looking at the ratio between the repetitiveness at subsequence 3 and at subsequence 2, we get an index of the entropy of the signal. So if A is equal to B, i.e. they're the same, then that's a highly predictable thing because at subsequence 2 and 3, we have the same number of matches. But then if A is much less than B, i.e. the signal becomes very non-repetitive once we get to subsequences of length 3, then the sample entropy is high. You asked for it, all right? There it is. Cool. But what's this whole multi-scale thing, right? So I told you that the entropy is increased at scale 1 and decreased at scale 5. It's actually quite simple. So at scale 1, we just have the raw time series that we had before. And we can, let's just take scale 2, for instance. You just take 2 elements at a time, and you take the mean of them. So for scale 5, you take 5 elements at a time, and you take a mean of them. So this is a compression of the data sequence. So what does this mean? Oh no, that's going to take so long to go back. Let's go to here. So conceptually, and this is why I think that this entropy metric is very exciting. We see increases in entropy at scale 1. That means that moment by moment, the entropy in the brain is increasing. 1 second, your brain is over here, and then it's over here, then it's over here, in a highly unpredictable way. And this is a little bit intuitive with the high-dose psychedelic state, right? It's very moving over the place all the time. But when we go to scale 5 and we zoom out a little bit and we look at the brain activity, all of a sudden, it's more predictable. It's much more predictable, in fact. And so this, I think, is an interesting and has not been shown elsewhere component of psychedelic action on the brain, that we're increasing the entropy moment by moment, but we're increasing the predictability, we're decreasing the entropy when we look on a longer time scale. I think that's pretty cool. So, we had, if you remember, 20 minutes ago, we had all of these previous findings, 12 different papers, and of course they have their own findings. So, from the static connectivity ones, there was 4, and all of them showed some increases in entropy. Our findings show that we don't replicate 3 of these, but for this path length distribution, this one that I'm still struggling to wrap my head around personally, we do have a weak to moderate association with psilocybin effects. For the dynamic connectivity estimates that have been previously published, 2 of them showed increases, and of those 2, we don't show any increases. And bear in mind, we have 5 times as many scans. I'm not writing these entropy metrics off entirely, but this is an indication that if there is an effect, it's going to be quite small. 2 of them reported null findings previously, and kind of confusingly, one of them we actually showed that there maybe is an association. It's just quite weak. We didn't talk about that so much today. And then 2 of them didn't report any findings because one of them looked at lasting changes, like are there changes in brain entropy a month later? I wouldn't expect that to be the case. But this one was this edgewise dynamic conditional correlation entropy that we showed was really increased. So the connectivity is changing rapidly over the course of the scan. And this was a real candidate biomarker. Finally, for the dynamic activity, this multi-scale sample entropy that I just spent 15 minutes describing, the previous data also showed increases at the short time scales, scales 1, 2, and 3, and then decreases at the long time scales, which is exactly what we show. And that's pretty exciting, because that is the first actual replication in psychedelic neuroscience. There was also something else with the bold complexity. Let's not talk about it today. Okay, so we have the Copenhagen Brain Entropy Toolbox that we've prepared from these 12 different entropy metrics. And what we've done is we've posted it on GitHub, which is just a repository for code online. It's MATLAB code. And it's openly accessible, and you can use it for any of your data. So we've now got collaborators at University of Copenhagen, Maastricht, Cornell, and at Leiden. These handsome gentlemen have been applying the Copenhagen Brain Entropy Toolbox to their own data. So we're going from a place where 6 months ago there was literally 0 replication in the space, to in about a year I expect that we'll have seen 5 different papers articulating the same entropy metrics on different data sets. And in fact, one of them has finished their analysis pipelines, David, and we've shown a lot of things have been replicating. So the sample entropy increased at short scales, decreased at long scales. The dynamic conditional correlation increased across the whole brain, except where? In the motor cortex. Might actually be real. And he's also actually shown a couple other replications. So, what are my conclusions? We've been stuck in phase 1 for psychedelic neuroimaging for just over 10 years now. And I think that it's time for us to move into phase 2, hypothesis testing. And that doesn't just mean, thank you, that doesn't just mean applying the same methods, but implying more rigorous trial designs, trying to work out whether these metrics, are they specific to psychedelics? Because actually, when I get people in, they're quite tired in the morning. When they get the psilocybin, they're really awake. And then in the evening, they're quite tired again. Maybe we're just indexing wakefulness, right? So I should have some negative controls in there, something that doesn't increase the richness of the conscious state, but contains some of the other components, so I can control what is specific to the psychedelics. Sorry. Specific to the psychedelics, because that might end up being what's specific to the therapeutic effects. And then we can see whether various antagonists, like ketanserin that block the 2A receptor, could block these effects or not. The fact that we're still in phase 1 means that I get a little bit frustrated and just like an arrogant, annoying scientist when magazines like Time say, here's what LSD does to the brain. Because, I mean, we got a grant proposal rejected recently because someone said, why do you need to measure the effects of psychedelics in the brain? They already did it. It's published in Nature Medicine. Like, we've done it. And that's the equivalent of like trying a drug in 8 people and being like, that's an effective antidepressant. Get it to the people. Get it out there. So we should be integral scientists and stand up to Time magazine and be like, no, we are not even close. We haven't tested any of these hypotheses yet. Thanks. All right, I didn't expect that. Okay, nice. So previously, sites have been sharing their data online, and that's awesome. If you remember, if you look at the review, about between a third and a half of all the neuroimaging studies that have been published to date have actually just used the same exact data set, but that's because the Imperial Group, power to them, just posted that data set on the internet, and master's students across the entire world went, hey, I can do a master's thesis with that, and have just analyzed the hell out of that data set. That's awesome, but now we need to turn the tables a little bit, and instead of applying 50 different metrics to the same data set, we need to start applying one metric to 50 data sets and turn that over. So that's we hope that we can contribute with the Copenhagen Brain Entropy Toolbox. It's an open repository. My inbox is open. If you have a new entropy metric that you want to add, we're super open to it. If you want to make another complementary toolbox that tests, say, the thalamic gating hypothesis or one of the other hypotheses in the space, that would be awesome. That's exactly what we want in the space. So we want to work with researchers who are coming up with these new methods. This has all been a little bit negative so far, so what I do want to say is that we have identified what I think are some really promising biomarkers in this space. We show these increases in path-length distribution, which I don't understand, but they've replicated across 2 sites, right? And 3, actually, if you include David's data. We see these increases in dynamic conditional correlation distribution that I think can help us to understand how our brain is working during these sessions. And then these increases in decreases in short-scale predictability and increases in long-scale predictability. I think those really tell us a lot about how the brain could be working, but it could. Finally, I want to end on this note of saying that solving what I'm maybe dubbing the psychedelic brain problem, what are the specific effects of psychedelics on the brain? It has a lot of implications within psychedelic science. We saw some great presentations earlier from Dr. Mithofer, who put up a bunch of fMRI findings. And that's because brain imaging, although it doesn't directly contribute to the approval process, it allows us to form this narrative where when we speak to a new physician in the space, or we speak to a regulatory body, or when we speak to the public, we can say, hey, psychedelics do this to the brain, and the whole thing makes a lot more sense than if we just said, look, they work, they're antidepressant, we don't know why, but they do. When we have mechanistic data, we have a much, much stronger case. But this goes far beyond psychedelic science as well. Psychedelics perturb conscious and conscious experiences, cognitive experiences, affective experiences in a very profound way. And in order to better understand a complex system like the brain, we need tools that alter that system. And so the implications go into all of affective neuroscience and all of cognitive science as well, if we can get a handle on the psychedelic brain problem. All right. This is the team that have helped to collect all this data and analyze all this, and I obviously couldn't do anything without them. I'm here just as an emissary for this big group of wonderful people who've done just terrific work. I specifically want to highlight Anders Olsen, who made and maintains the GitHub repo for CopBet, and then my supervisors, Gita and Patrick, and then Martin, who helped set up all of this studies. I want to actually end this time, I realize I've said that 2 or 3 times, with this quote from one of our participants. He said, I think it's absurd that we try to examine this phenomenon, that we're scanning my brain to figure out what's happening. I know we can't understand it, that we can't put an equation on it and figure it out. I feel it is human arrogance trying to tame all the beauty. I think, scan me then. We won't get any closer to the truth. And I love to say that when I last put up this quote, I was sort of like, you know what, maybe. But actually, we're getting there, man. Like, we're actually getting there. So I am enheartened, so that's not a word, by all of this work and all of this team. And so I really think that we will get closer to the truth. Thank you.
Excellent. That was truly excellent. And I'm sure that all of you in the room agree with me, because we're literally right now at 6:14 in the evening, and you guys just gave a round of applause, basically 8 o'clock in the morning. So that's just to show you how great this topic was. Thank you so much. We're going to move on to some questions for you.
Yeah, please. I'd love it.
Yeah, great. Yeah. And since we're caught up in time and everything, we do have a good 15 minutes for questions. I'm really happy to announce that. So let's start with the process. I see somebody over there. No? Okay.
Are they both waiting? Hi. Sorry. Thank you again. Amazing talk, very entertaining also. I love that.
Thanks.
My question is, you said that, like, seeing that there's an increase in long-term predictability, you have an idea what this could mean. What is your idea of what this could mean for how the brain works under psychedelics? Like what does it do to our perception, basically, and our way of thinking?
You're referring to the different samples, entropy scales?
Yes.
Here. So how does this affect how we should communicate this possibly to a patient, right, or to a physician? Well, you could say that the psychedelic state at its surface, if we sampled someone every second, right, and we just said, what about now? What do you think about now? What do you think about now? Obviously, like, the constraints of speech would limit that. But if we could just look at that, which is kind of what we do with fMRI, you would see that it's changing rapidly. So we can prepare people and say, hey, when you're in the psychedelic state, you might be thinking one thing one moment, and then, boom, another thought comes into your mind, another thought comes into your mind, or the visual field is constantly changing, right? But then we can also say, but don't worry too much. Because actually, if you zoom out a little bit and look at a wider time scale, you might find that it's actually very under control. Your brain state is not going to fly off the handle all of a sudden, just because it's changing a lot moment by moment. Like I say, I wouldn't currently say that to a patient or a physician. If this finding is replicated over and over again and in more rigorous design and in more rigorous conditions, then that's the sort of thing that we could start saying. But I wouldn't say it yet.
Yeah, thank you.
Another question?
Thank you. Beautiful talk. Thank you very much. You present these results about path length distribution effects, and you were wondering how to contextualize them. Did you came across the Giulio Tononi's theory, integrated information theory of consciousness?
Isn't that pseudoscience? Isn't that? Did you guys see that? Sorry,
it's been criticized indeed, but like I think there's some evidence in coma patients as compared to awake that indeed the path length is a marker of levels of consciousness.
So I have two comments. One, I just want to condition my previous statement on, there was a bioRxiv paper called Integrated Information Theory is Pseudoscience that came out like a month ago, and everyone got really mad about it. I don't have any opinions on IAT. I'm not really a consciousness researcher. Secondly, as to your point about changes in path length, so what they've shown, right, is that in states of minimal consciousness, people have increased path lengths, right?
Decreased
path lengths.
And less variability as well, as far as I know.
Okay,
so this would fit to your findings, essentially.
Right? Yeah, so what I've seen largely in the space is that people report left and rightward shifts of path length. But if you say there's also an increase in the variability of the path length, like the width of the path length histogram?
Maybe it's a way to look in it, because they have this measure of phi, essentially, also an information theoretical measure. I mean, maybe it helps you. That's just one idea I want to give.
Honestly, I'd have to look at their methods in a little bit more detail to be able to comment to how ours compare. If we've learned anything from this project, it's specifically how you do your calculations matters a lot. So when we've tried to actually compare our findings to other findings in the space, we've found out that they've done their Hilbert transform differently to ours, and then when we try that, our results change dramatically. And so, like I say, without knowing exactly the methods, I'm not sure that I can comment on the comparison between our findings.
I think there's one there, up there.
Thanks for the great talk. I wanted to ask you, so this is great, we have a metric now that can allow us to look within the brain and what's happening, but one thing we also know that the set and setting of a psychedelic experience is crucial for the healing process or the experience it has, and probably affects neurobiological activity. Given that the set and setting here is an MRI scanner, do you think this is an accurate representation of what people are going through during the psychedelic-assisted therapy sessions? Or can you think of ways to mimic better set and setting? Can the MRI machines make nice nature sounds instead of beeps? What's your take on this?
So I have two comments on this. The first thing I would say is that while I agree that, for example, the old wave of psychedelic studies where people were administered drugs without knowing about it, or in terrifying cold hospital rooms, and that had a lot of negative effects, we have some implication there that the set and setting is really important, right, for safety. In the modern wave, and without going as far as sort of tricking people, we have done 0 head-to-head comparisons of different set and settings and their impact on long-term outcomes. So we're running a study where we're doing half of the people getting music, half of the people not getting music. And that's the first time that we've ever actually looked at the impact of set and setting. It's very intuitive. It makes a lot of sense from a personal point of view, from a real-world point of view. But we don't actually know whether the set and setting has an implication for the lasting effects. Surely it has some implication for the acute effects. The participants tripping in the scanner, compared to our participants that tripped in our comfortable treatment room with the nice speakers, had slightly lower mystical experience questionnaire scores. They were slightly less intense in their effects. Apart from that, they're almost indistinguishable. I couldn't train, I used some qualitative data and tried to train something to distinguish out the different ones, and the only thing that I could use that distinguished them is that people who were in the scanner used the word scanner in the report. Otherwise, the effects are pretty much exactly the same. This also brings me, you've just led me into a nice point here, which I think that the healthy people, and even potentially people in a scanner, can be a useful model in this case. Because healthy people seem to have pretty much the same psychedelic experience as people on, psychiatric patients. So they're a useful model, nonetheless. And then just because they're in a scanner also doesn't seem to affect the experience that much. So I'll stand by healthy people in a scanner as being a good model of what's going on in the brain of patients in a treatment room. Because the psychedelics are just so strong, especially these higher doses.
Thank you.
So I wanted to compliment your explanation. Oh, I'm right here.
What's up?
Sorry. I wanted to compliment your explanation of the math. That was really incredible. I'm not a math person, but I found it incredibly interesting.
Thanks.
So I had two questions that I think are a little bit basic, but I just wanted some clarification. Do you think any of the differences in what you saw between old studies with different measures and your current measure is anything about differences in MRI technology or coding technology developments? And then my second question is, what is the actual time scale difference of the scale 1 versus scale 5? Because you say like long term, but what does long term mean?
Cool. Okay. So one of the strengths and limitations of our study is that our 28 people were scanned on 2 different scanners, one of which had very similar scanning parameters to a lot of the previous data, and one of which had more modern scanning parameters. When we look at the effects of those, of the effect of scanner, we see that there's some effect on the path length distribution, but by and large, actually, for all of our other findings, it doesn't really matter. So this was a nice validation for us that we can use quite independent scanner technology and still have the same outputs. So that's reassuring. However, for the ayahuasca datasets, which is 3 out of 4 of the static connectivity measures, they used quite a bizarre scanning setup, and they described their finding as bold-like. I don't want to get into the technicalities too much. There's quite a big difference there. So that could be different. The other ones, I think it's pretty nice, and our study design allowed us to test the effect of scanner as well. On the short versus long-term thing, the short scale is 4 seconds, and the long scale is 5 times 20 seconds. So, and because we see this interesting finding here, I think that we should possibly go further with this, right? Try use a higher sampling rate, see if we can get it down to like half a second, and then see whether that entropy is maybe even more increased, or maybe it's flatter at that level, and look at longer time scales as well. But what we did in this study is we exactly replicated previous methods as well as possible without going too exploratory with it. But I absolutely say that anyone who's out there sitting on data, upload the cupbet, change a couple parameters, and have a look at that, because I think that'll be really interesting.
Hi, so I had a question about the data collection. Mm-hmm. So maybe, have you guys tried to collect more qualitative data from the patients in order to like get what their experience was and compare that to the quantitative data, like to help with interpretation of all these metrics, like what they actually mean in the real world? Or?
Yeah, so qualitative data, we have collected qualitative data from all of these participants, where after their trip was done and they were sober again, we just gave them a big sheet and we asked them, hey, please describe your experience in as many words as you would like. And that's where some of these quotes that I showed you before have come from. So we have qualitative data, and we also have all these entropy metrics. I don't know how to plot a graph of like qualitativeness versus entropy. I'd love to. We can maybe try and do something where we like split people as like entropy people and non-entropy increasers, and then look at their qualitative data separately. Other than that, I'm a little stretched on how to do that. But we do have so we also ask them, what's your subjective drug intensity, right, at each time point? And I've done all of these regressions with subjective drug intensity instead of plasma drug levels. And all the results that I showed you today as being significant are also significant with subjective drug intensity. That's just on a scale from 0 to 10, how intense is your experience right now? We also have 5D ASC and MEQ and ego dissolution inventory and all of these other slightly higher dimensional questionnaires. The problem with those is that they say, at the peak of your experience, to what extent did you experience oceanic boundlessness, dread of ego dissolution? And because I have 5 scans, I don't know whether what they're experiencing at that time is what they've reported in the end, because maybe that peak happened at some other time, right? So because we don't have timestamps. So in future studies, now, instead of just asking how intense is your experience, we say good drug effects, bad drug effects, tension, anxiety, visual effects, and so on and so forth. And so now we're going to get better temporal resolution on the subjective effects, which should allow us to then understand better how the brain dynamics are related to the specific qualitative character of those effects.
Okay, can I ask a subsequent question?
Yeah.
So, would it be possible to ask the participant during the experience what they're feeling at the moment in order, like, to compare it with data?
Man.
Or would it mess with the data, like,
No, you can ask them. You can't ask them while the scan's going on, but you can ask them between. It can be a little difficult, though. So, like, we asked one person, they were in the scanner, right, and the scan finished, and we said, like, hey, are you having a good time? In Danish. And the guy goes, what is time? And we're like, man, this is going to be hard. People are super, super high. You can't get shit out of them, man.
fair enough.
We have time for one more question. Okay, well.
Yeah, so, I'll repeat the question. The question was, and correct me if I'm wrong here, was that we should look at different patient groups, effectively, so smoking cessation, alcoholics, opioid addicts, something like this. And I assume you mean look at how their brain entropy changes as a result of psychedelics being on board. And then also looking... Yeah, and intention. So individuals who want to just have a fun time versus people who really want to process some trauma or something, and how those are different. The first thing I would say is that we should first work to develop which biomarkers of brain entropy work generally. And then we can, once we get to that phase, we can start applying it to patient groups. My second question would be, do you think that the psychedelic experience is fundamentally different in different patient groups? And I think that's an unresolved question. We haven't got any head-to-head studies, same site, depression patients versus healthy people. My impression, just from being around it, from being around clinical trials as well, is that people pretty much have the same kinds of experiences. It's not like MDMA therapy, where people really process stuff. By and large, in our alcoholism studies, in our cluster headache studies, and in sort of friends of mine who've run anxiety, depression studies, people pretty much have psychedelic drug effects. And if they're not that different, it's going to be very difficult to see in fMRI because fMRI is not that sensitive a measure. So I worry about doing group comparisons. And fMRI has largely failed at, for example, comparing just depressed people with healthy people. We can find pretty much nothing that replicates, that separates depressed people from healthy people when we just put them in a scanner.
When you're solving a math problem, you're using certain parts of the brain. You know that, right?
Yeah. So specific functions can be articulated using fMRI, but population differences have been notoriously difficult to find and have cost hundreds of millions of dollars and have yielded effectively nothing thus far.
We have this great opportunity because we are a small conference And I know we have a lot of questions, but Drummond is actually here so that we can actually, engage all throughout the next 3 days. I think you're going to be here.
I'd love it if people come up and ask me
Drummond.
questions.
I think that would be great. We are now up for our break, and it's a very short break. It's a 30-minute break. And we're going to come back and we're going to have a session around, a panel around policy with some really great speakers. So please do come back. But as I said, all of our speakers are here, and so you can engage with them during the rest of the 3 days. Okay? Thank you very much.
Thanks very much, everyone. I
Thanks, everybody.
appreciate it.
Thank you.
Appreciate it a lot.